This video, The Atomic Blueprint Unlocking the Photovoltaic Effect, explores the fundamental science behind solar power. We will examine how a single photon of light can be transformed into an electron, generating direct current. The photovoltaic effect, discovered in 1839 by Edmond Becquerel, relies on crystalline silicon as its foundational semiconductor. Pure silicon is a poor conductor. To enhance conductivity, we use doping, injecting impurities to create two types of silicon. N-type silicon is doped with phosphorus, creating an excess of free negative electrons. P-type silicon is doped with boron, creating a deficiency of electrons, which are seen as mobile positive holes. Inside a PV cell, the N-type and P-type layers meet at the P-N junction, creating a permanent internal electric field. When a photon hits the cell with enough energy, it knocks an electron loose. The electric field forces the electron to the top surface, where it flows through an external circuit, powering your equipment. This is the photovoltaic effect in action. The P-N junction, also known as the depletion zone, acts as a subatomic one-way valve. Initially, free electrons and holes diffuse across the border, neutralizing each other. This migration leaves behind fixed charges, forming a barrier. This creates an internal electric field that prevents newly freed electrons from falling backward, strictly sweeping them to the N side. The band gap is the quantum hurdle that a photon must overcome. To free an electron in crystalline silicon, a photon must deliver exactly 1.12 electron volts of energy. Photons with less energy, like infrared light, are transmitted or reflected. Photons with much higher energy, like blue light, generate excess heat, losing energy through thermalization. A solar cell features an exploded blueprint of components. Key layers include the anti-reflective coating, a textured surface to trap light, and the N-type emitter and P-type base, where the primary absorption occurs. The cell is completed with front silver contacts to collect electrons and a rear aluminum contact to close the circuit. The PERC upgrade, or passivated emitter and rear cell technology, is an engineering solution to boost efficiency. The problem is that standard cells lose long wavelength light that passes through the silicon. The PERC solution adds a dielectric mirror stack, reflecting these escaping photons back into the cell for a second chance at absorption. Synthesis begins with the foundational rule. One photon across the 1.12 electron volts band gap frees exactly one electron. Millions of liberated electrons in a single silicon cell generate direct current. Modules combine 60 to 72 cells in series to output 300 to 400 plus watts. Finally, the direct current is transformed by an inverter into alternating current, ready for the grid.